Good morning. Welcome to today's class. In today's class, we'll be going through lesson number 6 of the 4th module. Okay, the theoretical part of this module is over. Was over in yesterday's class. From today on, we'll be solving some problems, and most of the problems we will be solving based on the laboratory tests. So you should remember all the laboratory tests, if not the procedure, at least the concepts. What load was applied in which direction, and what was measured, and how the things are plotted on the graph. Well, there are 4 tests. A direct shear test, second is triaxial test, and third is unconfined compression test. And finally, the 4th test is vane shear test. So in all the tests, we are drawing the graph. Okay, in the first 3 tests, okay, which are important tests, especially the first 2, direct shear test and triaxial test. They are very important. They are the most commonly, they are extensively used to find the shear strength or shear parameters of the soil. Unconfined test, it is only used for clay soils. And vane shear test, you can only find the shear strength through the torque applied. You cannot find shear parameters by vane shear test. That's why the first 2 tests, direct shear test and unconfined compression tests, they are commonly used. You should know these tests. And both the tests, we draw the graph. Okay, y-axis is shear stress, x-axis is normal stress. And in direct shear tests, okay, we are conducting 3 trials. Okay, for each trial, the normal stress is constant, and for that constant normal stress, we go on increasing the shear force, and we will measure the failure shear force. Let's say for the first trial, the failure shear stress was here, for the second, and for the third. So we'll get 3 points for 3 trials, and if you join all the 3 points through a straight line, then that is your Morse envelope. So this is direct shear test. And you can measure shear parameters by, okay, if you measure the intercept, that is cohesion, and if you measure the angle of envelope, that is our angle of internal friction. Coming to triaxial test. In triaxial test also we are drawing the graph, but in a slightly different way. X and y axis will be same. Y axis will be shear stress and x axis will be normal stress. But here, okay, for we are keeping the sample, okay, soil sample in the center of a container. We are filling the container with water and we are applying the vertical load. So the load is applied in all three directions. That's why the name triaxial test. So here, whatever stress, normal stress is applied in vertical direction, it is taken as sigma 1, and whatever vertical stress is applied in horizontal direction, it is taken as sigma 3, minor principal stress. So we are here we are conducting three trials. The important thing to remember here is we have soil sample. And initially the cell pressure is applied in all the direction. Then after applying the cell pressure, okay, after applying the pressure on water, which is called as which acts on the soil sample and which is called as cell pressure, okay, and it is denoted as sigma C. Sigma C is acting in all the direction. Okay, we will apply vertical load. We will apply vertical load, and the failure stress, the stress at which the sample fails, the vertical stress at which the sample fails, it is called as sigma D. That is deviator stress. So in horizontal direction, only cell pressure is acting, but in vertical direction, deviator stress as well as cell pressure is acting. So in vertical direction, both deviator stress and cell pressure is acting, and that's why okay, and in horizontal stress, in horizontal direction, only cell pressure is acting. So stress in the vertical direction becomes major, its magnitude will be more, and stress in the horizontal direction becomes minor principal stress as its magnitude will be lesser than the vertical stress. So for each trial, for the first trial, sigma C value will be constant throughout the test, and we'll go on increasing the vertical load, and we'll note down the failure vertical load and calculate the corresponding stress, failure stress, called as deviator stress. For the next trial, okay, we'll we'll change this cell pressure value and we'll keep it, we'll keep another value, but which is constant throughout the second trial. So we go on increasing the vertical stress until the sample fails, and we'll note down the failure stress or deviator stress. So 3 such trials are conducted. So we'll get 3 different values of, okay, sigma C and the corresponding failure stress or sigma D values. So we'll calculate sigma 1 and sigma 3 for 3 different cases. And that's why we know that, okay, this is for first case, sigma 3, let's say sigma 3, first case, and let's say this is sigma 3 for second case, and this is sigma 1 for second case. And this is sigma 3 for third case. And this is sigma 1 for third case. So we have sigma 3 comma sigma 1 for 3 different cases. So we'll draw 3 more circle. And then we'll draw a common tangent. With the scale, with the help of the scale, we'll draw a common tangent, which is tangential to all the 3 more circle, or at least 2 of them. Okay, so this is the Morse envelope, which is tangential to almost all the circles, and you can calculate the shear parameters. Okay, if you calculate the y-intercept, you will get cohesion, and if you calculate the angle, you will get angle of internal friction. So this is how shear parameters are calculated using shear test and triaxial test. Please remember this, or else you'll find it hard to solve the problems. And the problems, it will have theoretical solution as well as analytical solution. You can, if it is not mentioned in the question, you can solve it analytically or you can solve it graphically. But if it is asked in the question to solve graphically, then you have to solve graphically, you have to plot all the graph. Or if nothing is mentioned, then you may solve it analytically as well. Analytically, uh, I'll tell you when we are solving those problems. Okay, you need to remember some equations to solve those problems analytically. So let us solve some simple problems today. Okay, from next week onwards, that is Monday next week, we'll solve the problems based on the graphs, or else we'll solve problems today and okay, there is a big gap tomorrow, Friday, Saturday and Sunday, there will be a gap. So let us finish it continuously. So today we'll only solve very simple problems. Write down the first question. Okay. Okay, after writing the question, just raise your hand. We'll go to the solution part. Okay, we'll move to the solution part. Okay, I'll read the question. The stress at failure on the failure plane in a cohesionless soil mass where shear stress was equal to 4 kilonewton per meter square, normal stress is equal to 10 kilonewton per meter square. Determine the resultant stresses on the failure plane, angle of internal friction, and the angle of inclination of the failure plane to the major principal plane. Okay, they have analyzed a cohesionless soil mass element, and they have found out that uh, at failure the shear stress was 4 kilonewton per meter square, and at failure the normal stress was 10 kilonewton per meter square. So we'll write down the given data. Normal stress at failure was 10 kilonewton per meter square, and shear stress was 4 kilonewton per meter square. We have to determine the resultant stress, the angle of internal friction, and the angle of inclination of the failure plane. Now, there is no notation for resultant stress. We'll write it as resultant stress, but angle of internal friction of the soil, it is denoted as phi, and angle of inclination to the failure plane of the major principal plane, it is alpha. It is failure angle. So we have to determine resultant stress, phi and alpha. So resultant stress, it is very simple. Now normal stress, it is acting in vertical direction, and shear stress, we'll assume it is acting in horizontal direction. So the angle between normal stress and shear stress, I'll give you an example. If this is the soil mass, okay, this is my normal stress, and because of these normal stresses, shearing stresses are induced, and let's say it is horizontal. So because of these two stresses, what is the resultant stress? So the angle between these two stresses 90 degrees, and if the angle between two forces is 90 degree, the resultant force is given by under square root sigma square plus tau square. Uh, you have learned this concept in your first year, resultant of forces, okay, parallelogram law. Okay, when the two forces are perpendicular, okay, the resultant force is under square root f1 square plus f2 square, that is square summation of square of both the forces. So resultant stress is equal to under square root 4 square plus 10 square. Please calculate and tell me the answer.
10.7.
10.7.
10.7.
10.7 kilonewton per meter square. Okay. Next, we have to determine angle of internal friction. I told you from the graph. If this is my graph, okay, and y-axis is shear stress, x-axis is normal stress, and if you have, okay, this is your This is your angle of internal friction. So angle of any slope is nothing but, if you take this triangle, this is your y-axis and this is your x-axis. So phi is equal to now this phi is equal to, if you tan of phi is opposite divided by adjacent. So opposite is y-axis, that is shear stress, and adjacent is normal axis, that is sigma. So phi is equal to tan inverse of tau divided by sigma. Now shear stress is 4 and sigma is 10. So phi will be equal to tan inverse of 4 by 10, that is tan inverse of 0.4. What is the value of phi?
Sir, 21.8.
21.8 degrees. You can measure alpha, that is failure angle. Failure angle is given by 45 plus phi divided by 2. So phi is equal to 21.8 degrees. Alpha, so substitute that value here and you can easily calculate alpha. What is the value of alpha?
55.9.
55.9. Okay, value of alpha is 55.9. degrees. So this is analytical solution. You can solve the same problem graphically. Okay, just plot. You have to plot this on your graph sheet. If you don't have graph sheet, you can just plot it on paper. But in exam, you have to use graph sheet. Y-axis is shear stress, x-axis is normal stress. Okay, so shear stress is equal to 4, normal stress is equal to 10. So you have to assume some unit and we have to mark this point. Shear stress is equal to 4 kilonewton per meter square and normal stress is equal to 10 kilonewton per meter square. 7, 8, this is 9 and this is 10. So 4 units is 10. So the point lies here. Now this is the failure point. We have to draw strength envelope. Now how to draw strength envelope? Now in the question it is given that it is cohesion-less soil. Cohesion-less, that means C is equal to 0. I told you Morse envelope, this is Morse envelope. Y-intercept is equal to C. Okay, so if C is equal to 0, then this Morse envelope or strength envelope, it will start from origin. So for cohesion-less soil, the Morse envelope always starts from origin. So this is my Morse envelope, failure envelope, or strength envelope. For cohesion-less soil, cohesion-less, that is C is equal to 0. This envelope, it starts from 0. So this is my failure envelope or strength envelope. So I have to find the angle phi. Angle phi is if you take protractor and you can directly measure this angle, you will get angle phi. You will get this angle phi. Next, to draw to find the failure angle, you have to draw strength envelope. Sorry, you have to draw Morse circle. So to draw Morse circle, you have to. Okay, we know that Morse envelope is tangential to Morse circle. So at this point, draw a perpendicular. So this is a perpendicular line. Okay, drawn at failure point. This is failure point. 10,4. So we are drawing a perpendicular from the failure point to the x-axis. So this is the center of the circle, C. Now with C as center, and let's say this is failure point F. So with C as center, C as center and CF as radius. Draw a Morse circle. So if you draw a Morse circle, okay, so this is the Morse circle, and this angle, okay, this angle is 2 times alpha. So if you measure that angle with protractor, okay, and that will give us 2 alpha, and if you half it, you will get the you will get the value of alpha. And because we have drawn Morse circle, you can also calculate sigma 3. So this value is sigma 3. It is okay, 1 2 3 4 5 6 7. Okay, sigma 3 lies between 7 and 8, and okay, wherever the circle touches here, that is my sigma 1. So if you draw more envelope and more circle, you can calculate, okay, angle of internal friction phi. You can also calculate failure angle. You can calculate minor principal stress sigma 3 and major principal stress sigma 1. So this is graphical solution, and because it is not mentioned in the question how you have to find stresses, you can either follow analytical solution or you can follow graphical solution. So I hope I've understood both the solutions. This is a very simple problem. Okay, from the next class onwards, we'll solve the problems based on the laboratory tests. That is from Monday onwards. I'll in the afternoon class, that is at 2 o'clock, I will okay, we'll go through one experiment of surveying lab. Okay. Just the basics part. So in the afternoon 2 o'clock, I will be engaging the class that is surveying lab. Okay, we'll go through one or two exercises of surveying. 2 o'clock, don't join analysis of indeterminate structure class. Join surveying lab class at 2 o'clock in the afternoon. Okay, so we'll wind up today's class now. We'll meet in the afternoon at 2 o'clock for surveying practice lab. If anyone has any doubts regarding the problem, you can ask, or else you may leave and we'll meet again at 2 o'clock.